Okay. All right, good afternoon, everybody. My name's Tudor, and I'm here to give you a presentation on my design of an apparatus to examine subsurface cracks utilizing eddy current detection. My supervisors were Dr. Harville and Dr. Kay. Let's begin. So, the outline of this presentation will be as follows. We'll have an objective, some theoretical background, the methodology that I followed, the design requirements I came up with, as well as design options that were considered, coming up with the final design, results of that design that would verify that design, and continuing work. So, subsurface cracks. What are they and why are they important? So on the left here, you can see circled in red is a subsurface crack. This is a void or an imperfection in the material that was formed either through the manufacturing process or some impurity, something like that. And this essentially lowers the overall strength of the material. Now these are important because these can later develop to surface cracks, which in the industry could lead to piping failures and all that. So it's important to monitor these to form an effective aging management program for key components in the nuclear power industry. So the objectives. So beginning off with what I had to prove a concept of a sample assembly that I chose to model these subsurface cracks. After testing this proof of concept, I wanted to come up with a design for an apparatus to mimic subsurface cracks effectively in thin sheet metals. Moving forward, I've demonstrated the capabilities of eddy current detection in subsurface cracks with this apparatus. So, some theoretical background for any of you who aren't familiar with how eddy current works. This is exactly a very basic schematic of eddy current probes and how they interact with materials. So you have a probe in the middle. Alternating current is run through this thing. It generates a magnetic field, and this magnetic field itself induces a current in the conductive material that it comes in contact with. These eddy currents are the circular ones you see in turquoise. They are generated from the magnetic field, and they themselves generate their own magnetic fields in opposition to the coil's magnetic field, and these interact with the generated magnetic field from the coil. These interactions are dependent on the material properties of your conductive material, and they give you a very precise feedback on the material being examined. So by measuring the change in resistance and inductance in the coil, you can get some actual nice information on what you're looking at. Why eddy current is chosen. You can see that given the sample on the left is the example of aluminum that I was playing with for this design. Some of these cracks aren't actually, you're not able to detect them with other conventional methods like X-ray imaging. So on the right there you can see using the UA X-ray imager we have, I wasn't actually able to see the crack at all with any of the images that were produced. So it has some advantages when compared to other methods. So continuing forward with the background, eddy currents tend to concentrate near the surface adjacent to the coils, and they decrease in strength. They decrease in their strength as the distance increases from the coil. In the field, it's common practice to use what's known as a standard depth of penetration, or a sigma, and it's defined as 1 over the square root of pi times your frequency of your coil, your relative magnetic permeability, and your electrical conductivity. So it is common practice that the standard depth of penetration is set to around 37% of the maximum eddy current concentration. Beyond that, it's commonly, you're not going to get a nice signal, and you're not going to get a nice distinct differentiation of what you're looking at. There'll just be kind of a lot of noise that you will not be able to use. So rearranging that equation, we can get the optimal detecting frequency for materials of interest. As you can see in the chart below, we rearrange it and solve it for the F, and we get a nice chart of frequencies. So copper, aluminum, brass are the materials of interest, and it's 180, 110 roughly, and 36 kilohertz for the optimum frequency. And this is just a little example of what the crack assembly looks like. So, proof of concept. Moving forward, I just wanted to see what measuring subsurface cracks would be like in this very basic model that I just showed. So here we have a little experiment. We have the eddy current probe on the left, the aluminum sample in the middle, the eddy current controller, and the clamp assembly itself. For those that were present in last year's presentation with my group, this was one of the basic clamp assemblies we used to hold a material in place. And blown up on the right is the actual sample itself, with the middle one being the one that has the flaw. So moving forward, this is what I got. The actual graph is an actual representation of the size of the sample that was detected. So the X is how long it is, and the Y is how wide it is in centimeters. The blue represents the locations of the actual crack, so this is the actual flaw that penetrated the material through, and the orange is a scratch. So it's kind of like a dent or a defect. And the green are detection signals that were generated by the eddy current probe. So basically what happened is I would run this probe widthwise across the sample, and whenever it detected something, it would produce an audible beep. I would mark down the location of that beep, and then I'd superimpose it on this graph to see if it lined up with where the cracks and flaws are. So as you can see, there's kind of like a grouping in terms of how the points were generated. You can see the ones that have the solid circle around them, they look like air gaps. That's what I concluded. Just because of the distance from the crack and the kind of local nature of them. But these ones here that are in the dashed line are kind of almost right on to where the crack and flaw are. So this may be indicative of an actual crack or flaw detection of the probe. You'll also notice that this was at the 500 kilohertz frequency range. So this is just the self-calibrating function that the probe had when you just put it up to a material and it tries to come up with its own detection frequency for a material. But we'll see when I try my actual calculated frequency, we get different results that seem to be a lot more favorable. So you can see we get a nice better grouping, and you can see that some of the points that are offset still seem to just follow the same trend as the crack and the flaw. Reason being, as if you look closer, that these points are offset by around 5 millimeters, and this distance is actually almost exactly the diameter of the eddy current probe. So it's almost that the detection is offset by the diameter of the probe, so the fields are kind of just offset by that distance. So really good results. Moving forward, we get some design requirements. So first things first, we need to minimize air gaps between the sheets due to imperfect contact. These sheets are rolled or come from cans, so they're not flat to begin with. So there is going to be some air gaps generated when you try to put them together. The design shall allow for adjustable force, different sheet sizes, and all that, so make sure we can adjust it accordingly. Design shall be portable because the location of the probe and the controller are not in the lab downstairs, so I have to constantly move it back and forth. I want to make it as easy as possible. The design shall allow for a maximum exposed surface for detection, so we want to be able to generate a nice big crack that we can freely move the probe around to detect. And the design shall require a minimum cost for procurement. Enough said. So a little insight on how my brain works when I was trying to solve this problem, and some of the basic sketches I came up with, different clamp assemblies, different force application methods. There's a bunch of pros and cons for each one, but in the end I ended up using a hybrid of some of the ones that are shown here. And this is essentially the conceptual design. I apologize for the poor contrast issue with the scanner, but I'll show you a better picture in a sec. So here it is, nicknamed the rack because it resembles a medieval torture device. But essentially what you have here is you have your screw clamps on the side, right here, on each corner. And you have the adjustable wing nut and screws in each corner that allow you to either decrease or increase the tension that the clamps apply on the corners of the sample. The sample itself is taped off. These samples, when cut, are actually pretty sharp, so you don't want to prevent any harm that could arise from it. And then you have the wire guides that allow the screws to freely rotate without resulting in any twisting of the cable or anything like that. And then we have little correction clamps along the side to kind of minimize any local air gaps that may arise when you try to bond these things together with the tape and whatnot. So, verifying that this design is useful and works. So sample 1 is an aluminum sample. It's not the same one that I use in the proof of concept, but it's the same material. You can see it's 180 kilohertz, same optimum frequency, and it's a little picture of what it looked like. And the black dotted lines shows the actual the limits of detection with that diameter that we talked about earlier for 5 millimeters. So any points that essentially fall within this area can be considered as something indicative of a crack or a flaw in the sample. The ones here that seem to fall a little bit short, you can essentially attribute this to human error when actually measuring these things, because you're kind of just trying to recollect where exactly this probe signal was generated. So overall, really good results. Copper, same thing. You'll notice a little 3 off the side there, just due to deformation in the sample, but everything else seems to match what we want. And brass. Brass, also just awesome. Get a nice big grouping of points within the actual limits that we want. You'll notice that it's actually 70 kilohertz and not 40 kilohertz. This is due to the we're not essentially sure on what kind of composition this brass is made out of, and because of that, the material properties might vary from what we expected or when I calculated them. So this essentially shows the kind of skill of the operator that's required in the field when you're trying to detect something of unknown material composition and stuff like that. So concluding remarks, the proof of concept was demonstrated. I could show that you could successfully demonstrate or mimic subsurface cracks using the kind of sandwich assembly we talked about. Did design an apparatus to mimic these subsurface cracks in these thin sheet metals. It's repeatable and it's fairly accurate. And as well, I can demonstrate the capabilities of eddy current detection with this apparatus using the results I just showed. So, future work, I'd like to examine the future standard depth of penetration for alloys. I want to make sure that you can measure, you can accurately come up with these sigmas for alloys, because the ones that I tried to generate are a bit off due to the uncertainty in terms of material composition. The developed method for EC testing in pipe banks, just to make sure we can detect flaws through various pieces of voids, or like geometries that inherently incorporate some kind of void that's not necessarily a crack, and examine alternate NDT techniques for subsurface crack detection. So I'd like to thank all the NDL members, Adam, Jeffrey, Patrick, Sharman, Bradley, and Rob for allowing me to use their equipment and access to their lab, Dr. Sarvel and Dr. K for valuable support and guidance, as well as the LBB and MSL group for their continued support. Thank you for attending, and open up the floor for some questions. Gabriel.
I think it was the graph of the proof of concept. You showed some uncertainty lines.
Which one?
Right here. Are those uncertainty lines? Or?
Yes.
How did you come up with this?
Well, those are just basically the uncertainty values from a ruler. It's half the smallest amount of measurement, so they're essentially half a millimeter.
Do you compare results obtained to the expected results from prior studies?
Expected results, essentially that's what these points kind of are indicative of, right? You're kind of showing that if I operate at this frequency of which the literature review kind of hints at as this is the kind of frequency you want to operate the probe, you should be able to find something. And that's what these kind of points are kind of showing. In terms of other literature review, there's not much in terms of mimicking thin sheet metals. They're usually with concrete or other very big pieces of material. But these are fairly reasonable results. Here we go.
If you're using one of these in the field, you have no idea what the material is, what sort of algorithm or procedure would you take to optimize this process?
You'd want to talk very closely with the operator or whoever the owner is to actually get some kind of idea of what you're working with. Otherwise, you could just be spending all day just trying to guess what kind of material is, and it's really inefficient.
By varying that frequency?
Yeah, it'd be just too time consuming to just up and down it all day, as opposed to just getting some idea of what you're working with. Derwin?
I kind of noticed that your brass and copper sample were fairly within, fairly accurate.
Yes.
Relatively compared to your aluminum. Would this be due to the fact that, like the other one, the second trial?
Which one?
The second trial.
The second trial.
Like relative to, like compared the results to the trial 3 and 4.
Mm-hmm.
I noticed that it's a bit not as accurate as the other one. Is this due to the metal sample, or is this due to the frequency used to?
I'm a bit confused. Are you saying that you think these ones are more accurate than the trials 3 and 4, or the other way around?
Trial 3 and 4 were more accurate.
Oh yeah, that's what I was kind of hoping for, right? This was just a proof of concept to see what kind of issues would arise just from this kind of sample assembly, just putting these 3 together and seeing if a probe would actually pick up anything. And that's where you find all these kind of air gaps that start to pop up. So that's where I start to see, like, okay, if I can eliminate them, would I get better results? And as trials 3, 4, and 5 show, you think you do.
Last question? Anyone else? Ryan, you want to set up? Sure. Thank you.
Oh, thank you.